All right, welcome back, everyone. Last week we talked a bit about probability and the basic concepts and ideas of probability, how to calculate probability in some situations. This week we're going to expand that just a little bit further and talk a bit more about probability. And then in the next section, we're going to talk a bit about counting. And that may seem a little trivial, but you'll see what I'm talking about when we get there. This will all lead us back to statistics in a few weeks. But all of these concepts are really important to understanding how we're going to calculate a lot of things later. So in this section, we're going to talk about conditional probability. Conditional probability has to be considered whenever you have some knowledge of a condition related to some probability event. Okay? If we know more about the probability than just one particular thing, right, we need to adjust for the conditions of the probability, right? So when finding the probability of choosing a card from a deck, what's the probability that you would choose a face card given that the chosen card is red, right? So if you already know that the person chose a red card, right? Well, in a deck of cards, there are only 26 red cards. And if we want to find the probability of choosing a face card, if we know the card is red, well, there's 6 red face cards. And we can calculate the probability that way. But there are other ways to look at these same types of questions, and that's what we're going to look at now. Right? So if we want to look at the probability of choosing a face card given the chosen card is red, then what that means, let's say that A is the fact that it's red, and let's say that B is that it's a face card. Now, if we look back just a second ago, there are 6 red face cards out of 26 red cards. So we kind of have an idea of where this should go, but let's look at this a slightly different way. The probability of choosing both, let's see, the probability of choosing both A and B. And so what's the probability of choosing a red face card? Well, that's going to be what we just looked at a minute ago, 6 out of 26. Or, I'm sorry, 6 out of 52. Let me fix that real quick. So for the entire deck, I'm getting the two confused because you'll see why in a second. For the entire deck, the probability of choosing a red face card is 6 out of 52. There are 6 red face cards, 52 cards total. Okay, the probability of just choosing a red card, well, that's 26 out of 52. It's half. And we can reduce these, but I want to show you something real quick. And so we can determine that the probability of choosing B given A, right? So the probability of choosing a face card given that it's red is equal to the probability of A and B. So the probability of choosing both from the entire deck divided by the probability of just choosing A. Okay, and so if we do that, remember in the previous example, we did it just by counting how many cards there were. Okay, but if we do that here, right, and we just divide the fractions, right, when you divide these fractions, what you're going to wind up with is 6 over 26, exactly what we had a second ago. Now let's actually simplify this. If we divide by 2, 3 over 13, or 23.1%. So what you see here, even though there's division involved, is a form of the general multiplication rule for probabilities. Okay, we'll see that here in just a second. Let's look at a similar example. What's the probability that the wheel, here we have these slices and it's a spinner. We're going to spin the wheel, it's going to land on one of these 6 numbers. What's the probability that the wheel stops on a slice with a number less than 5? Okay, well, if we look, there are 1, 2, 3, 4 numbers less than 5. So 4 out of 6. And so there's a 2/3 chance that it lands on a slice with a probability less than 5. What's the probability that the wheel stops on a slice with a number less than 5, given that the wheel stops on a gray slice? Okay, so we already know that it's going to stop on one of the gray ones. Right, well, there's 1, 2, 3, 4 gray ones. Okay, but only 2 of them are less than 5. And so if we wanted to find that probability, well, then that would be 2 out of, we already know that it's going to stop on one of the gray ones, so there's only 4 options, 2 out of 4, or 1/2. Okay, but we can determine that probability from the beginning using that formula that I just showed you. Right, so the probability of, let's say, B is a number less than 5, and A is gray. So the probability of choosing a number less than 5, given that it's a gray tile, is going to be equal to the probability of choosing both. Okay, in this case, there are 2 out of 6, A and B, divided by the probability of A. There are 2 gray slices that are less than 5, so the probability of A and B is 2 out of 6. Okay, the probability of A, which is just using a gray slice, is 4 out of 6. And so that's going to reduce again to 2/4 or 1/2, just like we had just a minute ago. Okay, notice that you can do this either way, right, and get the same answer. There are some situations where one way is better than the other. That's why we're showing this with easy examples, because it can be more challenging later. Okay, so here's the general multiplication rule. Okay, and you may see some of these symbols that I write, the intersection symbol, rather than writing and all the time, but I tried to show you where all of these things work together, right? So what it all means. Right? So the probability of B given A, remember B and A are your probability events. And notice that we can determine those probabilities just by figuring out the number of ways for A and B to occur and the number of ways for A to occur. How do we figure out the number of ways that things occur? We count. And that's what we're going to get to in the next section. So let's take a look at this. A group of 118 doctors and nurses volunteered to run a health fair. Each volunteer worked 1 shift. The table below summarizes the data. That's this table here. Suppose a volunteer from the health fair is chosen at random. So we're randomly going to choose a person from one of these 118. And what's the probability that the volunteer is a nurse or worked the morning shift? Okay, well, we first need to remember what we're looking for here. Remember, this is the probability of, well, let's do this. A, we're going to say is nurse. And B, in this case, is morning shift. Okay, so remember, the probability of A or B is equal to the probability of A. This is from last week, plus the probability of B, minus the probability of A and B. So both. The probability of choosing a nurse 16 plus 24 plus 15. That's 55 out of 118. Okay, the probability of a morning shift. Here's the morning. That's 6. That's 22 over 118. Okay, minus the probability of both. Well, here's the both, where that overlaps, right? So 16 over 118. And that's going to give us, let's see, 55 plus 22 minus 16. Or 61 over 118. And if we divide that, it's about 0.520. So what's the probability that the volunteer that we randomly choose is a doctor, given that the volunteer worked the afternoon shift? And this word is important there, so watch for those in the questions that you're asked. If we want to find, let's see, A, we're going to call afternoon, and B will be doctor. And so if we want to find the probability of B given A, that should be a straight line. That's the probability of A and B divided by the probability of A. So A and B, well, that's an afternoon doctor, right? Well, here's an afternoon doctor. There's only 33 ways that that can occur. And so that's going to be 33 over 118. Okay, but remember, if you think back to the rule and the way these fractions have worked out, we're going to get 118 on the bottom too. So we really just need the number of ways that it can occur. So 33. Or how many doctors are in the afternoon? Okay, and then the probability of A, given that the volunteer worked the afternoon shift. So we want to know how many are, what's the probability of choosing the afternoon overall? And so that would be 33 plus 24, which is 57 over 118, or just 57. And so 33 divided by 57 will give you 0.58. So the probability of choosing a doctor, given that the volunteer worked in the afternoon, so given that you already know that condition, what's the probability of choosing a doctor? Well, it'll be 58%. Well, I left the question. We did this question on the last slide just a second ago. I just left that one in by accident. Let's look at another example. At a school's open house, t-shirts and sweatshirts were sold. Each item was purchased by either a student or a parent. Okay, so we've got a two-way frequency table. This is a contingency table like we talked about before. We have 70 items that were sold. Okay, we're going to let sweatshirt be the event that an item was randomly chosen from. Okay, so we're just letting sweatshirt and parent be A and B in this case. Okay, so what's the probability? Again, we don't have to, we can just write this way. What's the probability of choosing a parent? Right, well, there are, if we randomly choose one of these sales, 21 plus 14, that's 35 parents out of 70 items that are sold. And well, that's just 1/2 or 0.5. The probability of choosing a sweatshirt and a parent. Let me switch this around just a little bit. Probability of choosing a sweatshirt and a parent. Well, here's a sweatshirt and parent. There's how many of those there are, right? So there's 14 out of 70. That 0.2. Okay, now I want to find the probability. I'm going to change colors one more time here. That the random event that's chosen is a sweatshirt, given that we choose a parent, right? So B and A. We'll look at this, what we have over here. And the probability of B given A is just going to be the probability of choosing both A and B over the probability of A. Here's the probability of A and B. I may have them, okay. I'm sorry, I have them backwards in terms of what the letters should look like for the, it does matter. A and B, A. And so now the probability of A and B, or B and A in this case, is 0.2. The probability of A is 0.5. So the probability that you randomly choose a sweatshirt, given that your choice is a parent, is going to be 2/5, or 0.4, 40%. You can do some more with these types of problems. And the important thing here is to just pay attention to what the questions are asking you for, because there's a lot of information here, and that's why we work with these tables and things too, and why we talk about these probabilities. There's a lot of information in a single table. I mean, clearly you could answer lots of different questions like the ones we're going to answer here with any of these types of tables. So just remember that as we go along. So a sample of 368 students at a university is surveyed. The students are classified according to gender and major. The results are given in the table below. And we want to find and just answer these questions. So we're going to have these in a few pieces for the next few slides. What's the relative frequency of male students in the sample? Well, here's all the male students in the sample. We just need to add all of those up. 48 plus 24 plus 33 plus 47 plus 25 divided by 368 plus 24. Give me 1 second to add these things up. 177 over 368. And then when we divide, 0.481. So this is the relative frequency of males in the sample. Okay, what that just means is, you know, the number of males divided by the total. Okay. If we randomly select a student from the sample, what's the probability of selecting a male student? Well, that's interesting. In this case, the probability of selecting a male student, right? There are 177 male students out of 368 total possible choices, okay, which is 0.481. Is that how I wrote it? Yeah. I don't know if I went to 4 decimal places. 0.481 or 48.1%. So the relative frequency in the sample and the probability of randomly choosing that group from the sample are equal. Right? They're the same thing. Okay, so let's look at another one. What's the relative frequency of male business students in the sample? Well, male business students, there are 24. The relative frequency is going to be 24 out of 368. We divide that just to simplify. We get 0.065 or about 6.5% of the sample is male business students. So let's look at the next one. Among the engineering majors, find the relative frequency of those who happen to be female. Okay, so among the engineering majors in the sample, find the relative frequency of those who happen to be female. Here's all of our engineering students, okay, and it's only those folks that are in engineering that are in the sample. 31 of them are female, so 31 out of the total of 64. And if we reduce that, .484. So just remember to pay attention to what the question's asked for. Okay, relative frequencies are just a decimal, okay, or a percent, but they're giving you an idea of that amount compared to the other. Okay, but it is very similar to the probability of randomly choosing that person from that group, or that person in that group from the sample. When we have two events that are separate, so one probability event doesn't affect the other probability event. Okay, so let's say you flip a coin and you roll a die, right? The rolling of the die does not affect the coin flip. The coin flip doesn't affect the roll the die. Those two events are said to be independent. Okay, if the outcome of one does not affect the outcome of the other. Okay, one probability does not depend on the other one. Okay, conditional probabilities. Okay, would be a situation where it is not a conditional probability. Right? One probability and the other probability are separate from one another. Okay, so like I said, flipping a coin and rolling a die. If you want to determine the probability of A and B in that case, then you will just multiply the probabilities together. Okay, so what's the probability of, getting heads and then rolling a 5, right? Well, the probability of getting heads would be 1/2, 1 out of 2. The probability of rolling a 5 is 1 out of 6. And so that'd be 1 out of 12. And that would tell you the probability of getting both in those two separate events. And so at a factory, we produce pistons for cars. Machine 1 produces 707 satisfactory pistons and 303 that are unsatisfactory. You see the numbers for number 2. One piston from machine 1 and one piston from machine 2 are chosen at random. Okay, so we're choosing 2 pistons, one from each one, separate things. Okay, separate counts. Right, so independent events. What's the probability that the one from machine 1 is unsatisfactory and the one from machine 2 is satisfactory? Okay, well, in this case, the probability of machine 1 is unsatisfactory, so let's call that A. And unsatisfactory for machine 1, that's 303 divided by the total, which is 707 plus 303, 1010. The probability of B, the probability that we choose one from machine 2 that is satisfactory, well, there are 780 satisfactory ones out of 780 plus 220 out of 1,000. And so to find the probability of A and B, we just want to multiply these two together. And so we can do this all on a calculator here in just a second. So we don't have to reduce anything immediately. let's see, 303 divided by 1010 times 780 divided by 1000, 0.234, or 23.4% probability that you would choose one unsatisfactory from the first machine and one satisfactory from the second machine. Independent events are when the probability events do not affect one another. Okay, dependent events are where the probability of the second event depends on the probability of the first. Right, so imagine that you're choosing cards from a deck. You're going to choose multiple cards in a row, but you're not going to replace any of them. Right, so the first card you choose changes the probability of the next card that you choose, and so on. Okay, so when you deal with dependent events, where one affects the other, right? So you're doing things in some kind of order or something like that. Okay, then you have to consider how the probability changes at each step. Okay. So a pizza restaurant offers 13 different toppings. 5 of them are vegetarian, 8 of them are non-vegetarian. Customer selects the first topping at random and then selects the other at random from the remaining toppings. What's the probability that both of her selections are non-vegetarian? Okay. Well, there are 13 toppings total. Okay, 5 of them are vegetarian. So let's say the probability of A is the first choice. Let me change that just a little bit. So the probability of the first choice is going to be 5 out of 13, right? Because there are 5 vegetarian toppings. Oops, I'm doing it backwards. We're choosing non-vegetarian topic, so there's 8 out of 13. Okay, but now once we've chosen one, there's one less topping to choose from, and there's also one less non-vegetarian topic to choose from. Right, and so now on our second choice, if we're going to randomly pick one, there are only 7 more to choose from, right? And there are only 12 options because we've removed one of the toppings. And so to find the probability that both are non-vegetarian, right? So A and B in this case, or first and second, we're just going to do like we did a minute ago. We're still going to multiply them. 8 over 13 times 7 over 12. Okay, that will give us, not good enough to do that in my head, though I'm close. Put that in calculator. 0.359. It's 56 over 160, 156. But notice that the first choice impacts the second choice. There's less things we can choose from now. Let's look at another example of this. So in the game of blackjack, you dealt 2 cards from the deck, right? And they don't replace any of those cards. What's the probability that the first chosen card is a face card, okay, a jack, queen, or a king, and the second card is an ace? Okay, well, when nobody else is playing blackjack, it's just you, so we don't have to worry about losing any other cards. So the very first card that you choose, or the very first card that you're dealt, right, the probability of it being a face card. Okay, we're going to go with just the first and second choice here, just like we did in the last one, just to kind of show it. So the probability of our first choice, which in this case is going to be a face card, well, there are 12 face cards out of 52 cards. So the first card randomly chosen, we've got a 12 out of 52 chance of it being a face card. Okay. If we then want the second card that we choose to be an ace, okay, well, there are 4 aces. But now on our second choice, since we've chosen another card, or we've already chosen a card, right, we didn't put the first face card back into the deck. Right, let's just say we got the Queen of Hearts. Well, now this card is gone. Right, well, now there's only 51 to choose from. And so if we want to calculate this probability, that's a little tougher to do than the other one. 12 times 12 divided by 52 times 4 divided by 51. If I could type this into the calculator correctly. 0.018, or about 1.8%. With each successive dependent event, you have to adjust the probability for the one before it. If the events are not dependent, then you don't have to do that. And then you can just multiply them together. So whenever we sample from populations, okay, and this is how we're going to kind of link this a little back to stats here. And I'm going to show you again later where this probability, the discussion of dependent events and independent events can tell you something about probability, but we're not quite there yet. But there's 2 ways we can sample. We can sample objects with replacement, right? So we take things, we randomly choose something, and then we put it back. Randomly choose something again, then put it back. Okay? Or we can do it without replacement, where we take one thing and it's gone, and then we take the next thing and it's gone, right? So we do this over and over until we've sampled the entire group, right? Or whatever size we want to sample. When we sample from a population with replacement, right, the probability of each successive event does not change. That just means that we're putting everything back, right? It's like picking the card from the deck. If you pick a card from the deck and then put it back, the probability of choosing the next card is the same, right? It's not changed by the previous choice. Okay, so a student's backpack contains 8 blue pens and 7 red pens. 4 pens are randomly selected from the backpack in succession with replacement. Okay, after each draw, we put the pen back. What's the probability that all 4 selected are red? Okay, well, we've got 4 independent events here. Right? One does not affect the other. So to find the probability of 4 red pens, we are just going to multiply for each particular event. Right? 7 out of 15. For the first choice, we put it back. 7 out of 15 for the second choice, we put it back, so on. My parentheses are getting a little wonky here. Okay, that's 7 to the 4th power over 15 to the 4th power. And if you plug that into a calculator, 2401 over 50, 625, or 0.047. Okay, so there's about a 4.7% chance that if you put the red pen back every time, you're going to choose 4 pens that are red. Okay, notice that at each step, first, second, right, at each choice, the previous choice doesn't matter. Okay, that's what happens when we replace something in a sample. Okay, if we do this without replacement, okay, then the previous probability has to be adjusted, right? Just like we did with the cards. And so if we want to choose 4 red pens, but now we're not going to replace them each time, well, then the probability changes each time. Right, so on our first choice, it's still 7 over 15. Okay, but in the next choice, now we've removed one red pen and we've removed one pen overall. Now we only have 6 red pens that are left and 14 choices. On the next one, we'll only have 5 red pens that are left and with only 13 choices. Okay, and then 4 red pens with only 12 choices. Okay, and we could multiply all of this out. You get 840 over 32,760.026. Notice just in this problem, as we arrive at the end of this section, because in the next section, we're going to talk more about counting these types of things, right? And we're going to come back to talking about these ideas of samples, but I want you to notice one thing here in this last part of the problem, right? Notice how we're multiplying here. 7 times 6 times 5 times 4, 15 times 14 times 13 times 12. We're just counting down one number each time, right? And that's going to be something that we're going to use in the next section. I'm going to show you how to simplify some of this notation, and we're going to talk about how to count different situations when we're choosing different amounts of different things, and how to determine the number of outcomes in particular situations.